Okay guys, so we're back here. We're looking at this function down here, and I just asked Joseph, what is the x-intercept? He told me it's 2. Okay, so remember how to get that. Okay, he's realizing now that that might not be right, but what is it actually then? Right, there is none. Okay, because if you multiply this by x minus 3, this goes away, this is still 0. So we end up with 0 equals 2. What does this mean? No x-intercept. Which is perfectly possible, right? We've seen lots of graphs all the way back to grade 10 that don't have any x-intercepts. Right? One of them, you know, I could draw up here. You know, there's one. There's a basic one. X squared plus 1, right? Doesn't have any x-intercepts. Okay? So, can definitely happen. What happens algebraically when that occurs is you get something that doesn't make any sense. Okay? You get 0 equals 2. So that's not possible. So our y-intercept now. Alex, what's our y-intercept?
You plug 0 into x, so you get, so isn't it just 0?
No.
Oh, sorry, it's 2 over 3.
No.
Negative 2. My bad.
Okay. Any questions on that one? Alright, we're good there. Our asymptote. So let's go vertical asymptote. David.
3.
What's 3? Okay, careful. When you guys write vertical asymptotes, if you just write vertical asymptote 3, I'll say nope, because I don't know what that means. You have to write the equation, okay? You have to realize it's an x value. For all vertical asymptotes, they're always x equals. Okay, and the reason for that is because we have 2 over 0, right? Number over 0, we get a vertical asymptote. Okay, horizontal asymptote. Anthony? Y equals 2? What do you guys think? No? What was the condition again for horizontal asymptote? Let's go back to our review from 5.2. We have a horizontal asymptote only when the degree of P is less than or equal to the degree of Q. So the numerator is less than the degree of Q. Okay, yeah, that's true. So, do we agree with that?
Yeah. 0.
You guys remember this? Okay, so it was the one part that was left out. When the denominator has a greater degree, we have a horizontal asymptote at y equals 0. Okay, so denominator has a greater degree, we have a horizontal asymptote at y equals 0. Any questions? Okay. And positive and negative intervals, so we're going to write our numerator and our denominator and our result. And we write our ranges here. So remember, the ranges are going to be dictated by our x-intercepts, which there are none, as well as our vertical asymptotes, which there is one, so there's 3. So we go negative infinity to 3. Okay, so if this is the case, this is always positive, and this is going to be negative. So we have a negative interval Any questions? All right. So that's the first one. Let's just double check here everything that they got. So we had our domain at x cannot equal at positive 3. Our y-intercept at negative 2/3. Yes. No x-intercept. Yes. The line x is a vertical asymptote and y equals 0 is a horizontal asymptote. Okay. F at x negative when we go from negative 3, and it's positive when we go 3 to infinity. Any questions? All right, let's do the second one quite a bit quicker. Oh, sorry. I. Use these characteristics to sketch the graph. Okay, so when you go to sketch, the first thing that I always draw in is the vertical asymptote. Okay, it's kind of a really big defining line, right? It's almost like another axis. So I draw that in. Okay. So they have to decide how this is going to move, up or down. Okay. You might argue, looking at this graph, that you know that y equals 0 is a horizontal asymptote. So you could almost already argue that this has to go down because it's not going to cross the horizontal asymptote. Okay? But it's still important that you guys know how to figure this out. And it's just by plugging in values close to the vertical asymptote. Okay? So they plug in 3.1 and they're going from this side and they get 20. So they know that it has to be going up. Okay? They plug in 2.9, so we're on this side of the line, and we get a really negative number, so we know it's going down here. Okay, any questions? All right, from the graph, the function, and then finally the last question, it says, describe where the function is increasing or decreasing. So that, after we draw it, we just have to describe that. Okay, so remember, always reading from left to right, it's decreasing here, and it's also decreasing here. So the function is always decreasing. So from negative infinity to 3, and from 3 to infinity. Yeah.
How do you judge when it starts to turn? How do you like determine the exact value?
Where it turns here?
Yeah, like how do you know when you're drawing it out, right? When it turns, how do
Yeah.
you know where exactly it turns?
You don't.
You don't?
You don't know. So you could have drawn this like this. It's just a sketch, right? Just the information you're given. It's a good question because that's a key point, right? One way to tell where you're close is you can figure out this value, right? The y-intercept value. You can figure out. Okay, which we did, right? We had our y-intercept at negative 2/3 up here. So you know that point. Okay? But yeah, to answer your question, how do I determine if it crosses through there and then turns like that, or if it turns like that? I would say that one way to tell would be the degree of the function itself. If it's a really high degree, remember the turns are a lot sharper. Remember that? We know that, right? From y equals x squared, looks like this. You know, and y equals x to the exponent of 4, the turn looks like this. Okay? So if it's a much higher degree, Marco, you might argue that it has a much sharper turn. Okay? But yeah, you don't know exactly where it turns. All right. Second one. So let's just go through this with them. The first question says, what are the domain? So we have to figure out when can the denominator not be valid. So when 3x plus 4 is equal to 0, that's when it's going to be undefined. So that's what we need to set to equal to 0, 3x plus 4. That's how we get negative 4 over 3. Any questions about that? So it's a little different. It's not a straight up domain. You have to do a little simple equation before you find that out. Okay, so our domain cannot equal negative 3 over 4. Notice how that's going to be part of what we check when we go down here. It's going to be our key point because that point we cannot cross. Next, we want to find out our y-intercept. So we plug in x equals 0 and we get negative 1/2. X is 0 here. We get negative 2 over 3, which is negative 1/2. Next, we want to find out our x-intercept. So we plug in y equals 0 and we end up with x equals 2. Okay, so that's also going to be a key point. Finally, our vertical asymptote, we know is going to occur at x is equal to negative 3 over 4. because that again will give us a number over 0. So we end up with a vertical asymptote. And our horizontal asymptote, because they have the same degree, is going to be the coefficients divided. So 1 divided by 3. So we have a horizontal asymptote at 1 over 3. And finally, now we're going to determine when it's positive and when it's negative. We write the numerator and the denominator here and the product here. And our range is going to be negative 4 over 3 because that's a vertical asymptote. So that's going to be a divider. And positive 2 is going to be a divider because that's our x-intercept. So that's when we cross over from positive and negative. So we get all that information. We know it's positive here and we know it's negative in this range here.
So how do we get the horizontal asymptote?
The horizontal asymptote, because the degree is the same, x and x, we just divide the coefficients. So 1 divided by 3.
Oh.
Okay? And that's a rule we established last section. All right, so using this information, the first thing we do is we draw our horizontal and vertical asymptotes. So our horizontal is at y equals a third, and our vertical is at x equals negative 4 over 3. Once we draw those in, we're going to test values on either side of the vertical asymptotes to determine which way the graph is turning. Okay? If we know which way the graph is turning on the vertical asymptote, notice how we've already figured out which way it's turned on the horizontal asymptote. Right? You don't have to go in and substitute values of y to figure that out, because you're going to know this is up here, well it has to turn this way. Okay? Can't cross this line and it's going to turn there. Okay? So you only have to do the substitutions for the vertical asymptotes. Okay? All right, C, we're doing the same thing again. We set the denominator equal to 0 to find out where the vertical asymptotes are, as well as the domain. This time what we find when we set the denominator equal to 0, we get x is equal to 3. So that's our domain, but what we find when we search for the vertical asymptote, it's tempting so far to say that there's a vertical asymptote at x equals 3, but we notice when we plug it in, we get 0 on the numerator as well. So what's that tell us? It's a hole, right? So we know we have a hole, not a vertical asymptote, where x is equal to 3. Okay? Also, when we set y equal to 0 to find the x-intercept, what we find is that we get 0 equals negative 3. So we know there's no x-intercept again. Okay? The y-intercept, we sub in 0 for x, we get 1/2. All right, so we get this graph, and it's aligned with the equation y equals 1/2. And there's a hole at x equals 3. It has no vertical asymptotes or x-intercept. So there's only one interval to consider, negative infinity to infinity for any value. So that's important, right? We didn't have any vertical asymptotes, we had no x-intercepts, and we had no x-intercept. So it never crossed, we had no intervals to check. So when we tried to check our positive and negative intervals, that was our only interval. And what we established is that it's always positive. So in fact, our graph was just a horizontal line with that equation y equals 1/2, with a hole at 3. And finally, the function's neither increasing nor decreasing, it's constant over the entire domain. All right, the last problem we'll look at quickly, they use a graphing calculator. The function looks like this. It models the population. One thing you should notice, first thing that should come to mind when you look at the function, at least what comes to mind for me, is whether there's any horizontal asymptotes. I look at the degrees right away. Here you can see the degree is going to be the same. Once you multiply 30 times 7t, you're going to get 210. So 210 divided by 3, which is 70. So you're going to have a horizontal asymptote at y equals 70. You're going to have a discontinuity at 3t plus 2 is equal to 0. So t is going to be equal to negative 2/3. If you plug in negative 2/3 for t here, you'll find out that the numerator does not equal 0. So you'll get a vertical asymptote then at t equals -2/3. Okay, so that kind of stuff now should be starting to come naturally to you guys just by looking at the original functions. You should have a lot of thoughts about what it looked like. So there's that horizontal asymptote at y equals 70. It's right here again. Okay. And it looks like there's a vertical asymptote. So the vertical asymptote would be in the value of t. We plug in. Sorry, the x-intercept, we'd plug in a value of y equals 0, and the y-intercept, we plug in a value of x equals 0. So that would give us our y-intercept. All right, let's look at the summary. Okay, the graph's most rational functions of the form b over cx plus d and ax plus b over cx plus d have both a vertical asymptote and a horizontal asymptote. Okay, so the horizontal asymptote here is what? I don't even need to know the values of the coefficients. What's my horizontal asymptote here? Philip. Horizontal asymptote typically is what? You divide the coefficients when the degrees are the same, right? In this case, the degrees aren't the same, though. The denominator is higher. Yeah, so it's horizontal asymptote, but y equals 0. Okay? This one, horizontal asymptote at Mayfair, y equals what? Just give me the variable values. What would it be? Yeah, A over C. Okay, number 2. You can determine the equation of the vertical asymptote directly from the equation of the function by finding the 0 of the denominator. So you set the denominator equal to 0 and solve for x. Okay? So in this case, the vertical asymptote would be, Jesse? It would be negative d over c. Right? Because you got to divide this c out, right? Can you see that? It's a little out of focus. Okay, you can determine the equation of the horizontal asymptote directly from the equation of the function by examining the ratio of the leading coefficients. We talked about that. The sketch of the graph of a rational function, you can use the domain intercepts equation of asymptotes in positive and negative intervals. All right, we talked about that. Rational functions have a vertical asymptote defined by x is equal to negative d over c. So we just talked about that, and have a horizontal asymptote defined y equals 0. That's what we talked about up here. So we get that as an example. Okay. Most rational functions have a vertical asymptote defined by this. Okay, and that's from setting the denominator equal to 0, and a horizontal asymptote defined by a over c, which we determined up here. And there's another example. The exception occurs when the numerator and the denominator both contain a common linear factor. This results in the graph of a horizontal line that has a hole where the 0 of the common factor occurs. As a result, the graph has no asymptotes. For example, we have this. Okay, so that's because the numerator and the denominator are both 0 when you plug in x equals 2. So at x equals 2, we have a hole. Okay, and it becomes a linear line because you can see the x minus 2's cancel. You can just see that. It crosses out, and then y is just equal to 4. Any questions?